Thank you very much. Assalamualaikum warahmatullahi wabarakatuh. Today I will talk about the research that we've done so far. So actually this is based on undergraduate thesis of my student Erika Makanti, and actually I asked her to present this, but she's busy right now. So if you see Erika Makanti, so it looks like Italian descent, but actually not. She's from Beijing. So I asked her why you have like the Italian name Makanti, and she said that because my father is Matroji. She should have a another mat. Okay, I'm talking about the simulating the classical and relativistic equation of state of the star upon variation of the electron to baryon ratio. So actually, in my institution, Bogor Agricultural University, mostly in Department of Physics, research usually related to life sciences and so on. But sometimes, once in a while, you have a student that I want to do astrophysics, but because the curriculum, maybe it's not like in Universitas Indonesia, we don't have that sophisticated courses. So we only have like quantum mechanics, statistical physics, and then mathematical physics, and so on. So sometimes it's challenging to give them a topic related to the astrophysics. So, but when you do the searching and reference, there are some. Actually, some of the problems that still can be done by the undergraduate physics is related to solving the equation of state of the star, usually white dwarf stars. And this can be done. There are some papers from several institutions, compact star for undergraduate, neutron star for undergraduate, and so on. And here we try to do that, the same thing. But usually people talk about the white dwarf star with the ratio between the electron to baryon ratio about 0.5. But we haven't seen that. Why not we just try to vary the electron to baryon ratio? And I think it's a good numerical project for her. So what we did in this project is modeling the equation of state of the star using classical and relativistic using Kalman and Markov approach. And then varying the value of electron baryon ratio and see the consequences. So like as you know, the evolution of the star shown by this map has two master diagrams. So different stars, different size, they have a different luminosity, and they also have a different fate. So for example, so depend on the initial mass. So it could be a neutron star, black hole, or a white dwarf, brown dwarf, and so on. So as the stars getting older, so the fusion reaction inside the star make them heavy. So it's like cars. Getting older, getting fat, something like that. And at the end, yeah, the stability of the star sustained by the hydrodynamic equilibrium between the gravity that always attraction tries to collapse the star, and also the Pauli pressure. You know the larangan Pauli. Pauli exclusion, yeah. That's why the gravitational attraction and then Pauli pressure. And for white dwarf, usually the Pauli pressure calculated using the electronic fermionic pressure. And the classical equation of state of the star, the Newtonian star, is simply just like this: the pressure as a function of distance from the center of the star, Gm, R, rho r, and the mass density of the mass of the star, like this. So it's a Newtonian. And also it's interesting, actually the order of this in calculation is very important. Actually my students stuck for about 2 or 3 months, because when look at the paper, okay, this is the equation, so let's make a code and try to run it, and it's the result is always there's no result. I mean the calculation is it's not working. So yeah, it's confident. So, but when we put this up, the MR over dr and then dpr, the second calculation, it works. So it's the order is very important, because how we create pressure without mass. So even it's a simple problem, but this is a good pedagogical exercise for the undergraduate students. And then the general equation of test can be, long story short. So you put everything on it. So the relativistic and non-relativistic, you have a little bit soft, and you do the scaling. This is already scaled equation. So you have what you call a polytropic equation. So for the non-relativistic and relativistic, the difference is just 5/3 and 4/3 here. So using this equation and solve using MATLAB and put in the right order, so you will get the result. So this is the result. So actually this has been done by many institutions before, but usually they just do the white cloth YE over 5. So this is go to the limit of Chandrasekhar limit, which is 1.4 something. But here we try to vary the YE, the electron to baryon ratio, from 0.1 to 1, and this is the result. And for the non-relativistic, you see the scale is different, the 10 to the 16, 10 to the 9. And what's important was this YE 0.1, because in neutron star, usually neutron star is assumed as has a 90% neutron and 10% proton. So if we assume that neutron star consists of that 90% neutron and 10% proton, so we have YE is 0.1. So we can grossly assume, using that gross assumption, we can predict what was the neutron star here. And this is now the result using, we can calculate the critical radius as a function of YE. So it looks like that for the, suppose for the simplified version of neutron star, which is 0.1, so in the relativistic case, the critical radius is small. The neutron star is really small, and then for the non-relativistic, a little bit bigger. And then we also compare the star mass, the mass of the star in relativistic and non-relativistic as a function of YE, and then also the density of the star. So when you have a simplified version of neutron star 0.1, so you see that the density is high, and that's what's expected from a neutron star. So the conclusion of this research, the increasing value of YE will produce a bigger critical mass and radius, but smaller density of the star. And then using a gross assumption that neutron star can be assumed using this white dwarf model. With the YE 0.1, the radius is 1200 kilometers, and this is of course off by 2 orders. So the radius of the neutron star, I think it's around 9 to 12 kilometers. So we have almost 100 more. And the critical mass is 0.05 mass of the star, which is off by 28 times. Because for the neutron star with 12 kilometers, we have 1.4 mass of the sun. So it's off by 28 times. And this inaccuracy is expected due to the incorrect assumption. Because using the white dwarf assumption, which is using electron Pauli pressure instead of neutron Pauli pressure, of course it's inaccurate. So, but even though inaccurate, but this result still pedagogically reflects the same feature expected for the neutron star. What is that? Having a smaller radius and higher density. So I think that's all. Thank you.
I think we can take time still for
Yes.
Well, I'm curious about when we think that the neutron star is in relativistic or not. So, what I mean in a real life, does the neutron star itself?
Yeah, actually, what we did here is using a gross assumption. We just solved the polytropic equation. Usually, this equation just for white dwarf. Using YE 0.5. But we're curious, what about if we change YE from 0.1 to 1? and then we just assume that okay, neutrons are usually 90% consists of neutron and 10% proton. So it means that like 10% electron and 90% or 100%. 0.1, the electron to baryon ratio 10% over 0.1 divided by 1 is 0.1, right? So we just using that gross assumption. Of course, like I said before, it's inaccurate. They just play around. So this is an undergraduate project. Try to play with the astrophysics thing. So how to calculate the polytropic equation, how to derive that, how to deal with the top equation, just that. So of course, this is really inaccurate. I mean, if you want to do serious astrophysics research, you have to learn more, and usually it's in for graduate students, maybe that's good. Yeah. So for me, if they can recreate they can calculate, they can make a code, they can calculate, derive the equation, and then running it. That's enough for me, for undergraduate level. Yeah.
Any more questions? Actually, I also have similar wonder about why you use quantum mechanics instead of classical theory.
So classical here we are using quantum mechanics. So the relativistic and non-relativistic. Relativistic means you use the general relativity.
Yeah, I mean
the top equation.
You simply solve classical mechanical equations without any quantum mechanical statement.
Actually, yeah. I didn't know that actually when we from here, this is the general, this is still Newtonian, but when you're dealing with the real equation of state, long story short, there's a quantum mechanics calculation. Of course, you have to consider everything. You have to consider fermion, boson, fermion, calculate using statistical mechanics to end up with this equation.
Okay. I was just wondering if at some step you actually implement how either Schrodinger or Dirac equations that are transformed into some sort of different form, and then after that you solve it. Is it something like that?
Yeah, when you calculate the Pauli pressure, electron, fermion, you do the statistical system.
Thank you. Next speaker, our result.